Hello, good morning.
Good morning. We'll start in a couple of minutes. Let's just wait for some more participants. Good morning and welcome everybody. I'll wait for, let's say, 2 more minutes for late comers and then we'll get started. All right, let's get started with it. So I'll keep an eye on the chat so you can ask questions. If you do, please use the general chat, so not the one for the moderator, but just the general chat, the general channel, because that's the one I'll keep an eye on. I'll also start sharing my screen. Okay, and let's pull up the slides. All right. So, try to enlarge this a little bit more. Okay, that's better. Okay. Um, so normally You can see the slides. And I move that so that it's not in the way. Okay, let's get back to the chat here. And oh, come on, back to the slides. Okay, so containers for HPC. You can find the slides and so on this particular GitHub site. So I'll also post the link in the chat. But when you get there, this is what you get to see. So it's a small website that contains information about this training and a little bit of schedule and also the training material. And of course, if you click the link here, you go to the GitHub repository that contains, among other things, slides for this particular session. Okay, so let's paste that in the chat. And then that's out of the way as well. Okay, so let's start with a little introduction and some motivation. So a lot of things happen in the world of containers. You're quite aware of that, no doubt. And of course, the most popular way of using containers is most likely still Docker. But on HPC systems, this is a bit of an issue because the problem is that to use Docker containers, you need elevated privileges. So basically, you need more privileges than a typical system HPC system administrator is willing to give you. So that's an issue. But luckily, and for quite a while, there has been Singularity. So Singularity is a different type of container. And the big advantage of it with respect to HPC is that it does not require elevated privileges. So any user on any system can run a Singularity container without having to have root access. So that's a very nice thing. So Singularity was originally developed at Berkeley Lab and has been, well, there is a spin-off now, but there's also still a community effort. So the situation is a bit weird at the moment, but okay. So on VSC infrastructure, you can typically use Singularity without any issues as an alternative to Docker and to Shifter. Okay, so containers in general. There are good things, there are bad things. The good thing, obviously, is that containers are quite useful. They allow you to resolve some dependency chains that are sometimes quite hard to resolve. So that can be, for instance, for X11 applications that can have rather horrendous amounts of dependencies, which are difficult to deal with on typical HPC systems. And also, of course, if you need to run legacy applications, well, 32 bits, even, well, it happens fairly often that HPC systems simply don't offer support directly for 32-bit applications, since those run less efficiently, and hence typically we don't really, let's say, encourage you to use them. But if you really have to, for whatever reason, you actually can using containers. Another motivation which you see fairly often, also in industry, is that it allows to make your workflow portable across different systems. So for instance, there is a company that uses the VSC infrastructure for R&D purposes and for proof of concepts, but they run their production system on AWS, so at Amazon. And they do that using the same containers. So it's the same workflow, it's portable and compatible with different systems. So that's another possible motivation to do that. The bad thing is that containers may pose a security risk, but again, that is where Singularity comes in. So typically you need to escalate privileges, which we don't want to do. So that's a bit of an issue. The reason for that is that it potentially offers you access to the entire file system, and that's of course a no-go on a multi-tenant HPC system. So that's why Singularity is actually a very nice thing. So this is a bit the architecture of Singularity. It's just been taken from the Singularity documentation, but the important thing is that there is no escalation of privileges. So basically, on the diagram on the right, you see that you have the normal applications running on your system, and those are installed on the root file system. And on the other hand, you have applications running within Singularity container, and that just runs on top of the Linux kernel without having to any need for escalated privileges. Okay, so what's a Singularity image? It's a single file. And that is also something that distinguishes it from its competitors like Docker. So in Docker, you have images that are layered and they are cached somewhere, and it's not really obvious. While with Singularity, Singularity, the container is just a file. It contains everything. And that means operating system components, which are required to run the applications in your container, system libraries, application libraries, the application themselves, and potentially, but normally you don't do that, but it's possible in some circumstances, also data, which is required to run your application. Okay, so that is different from Docker, and that has advantages. So one of the advantages is that as long as you have that file, you can actually run your container everywhere, and you can run it exactly as you ran it the first time. So that is actually a very good thing with respect to reproducibility. We'll talk about reproducibility later in a bit more detail as well, but this is already a nice thing. Just archive your file, your image file, and you can just run it anywhere you want in the exact same way as you did before. So that's a good thing. So creation of Singularity images can be done on any machine. You don't need elevated privileges, so that's a good thing. But you do need root privileges. So basically, that means that a Singularity built on HPC systems is typically not what you do. You typically just do it either on your laptop, where obviously you have any privileges you require, or it can also be done remotely on the Scilab's website, which is actually pretty neat. The deployment, so it runs on any Linux machine where Singularity is installed, and at that point, when you just run it, you don't need any root privileges. So that makes it quite useful on HPC systems. Installing Singularity on your own machine is really straightforward. You can, if you're on an Ubuntu system, then you can just use opt, or if you have another system like Red Hat or CentOS, you can use yum. You're basically your package manager. Just opt install Singularity and you're good to go. So that's quite straightforward. If you really, really need to, you can build it from source, but you will need some things like SquashFS and of course Fuse on which that file system is running. Okay, so any questions at this point before we dive into the technical details and really start by creating an image?
Hi, this is Naeem. I was just wondering, is it possible to create Singularity files on Windows operating system?
Yes. So basically, if you have the Windows system for Linux,
Yeah,
which now is very easy to install, then it is just a matter of installing Singularity within the Linux distribution you're using, which would most likely be Ubuntu. And
yeah,
then indeed you can just create your images on the WSL, which is part of your Windows operating system.
yeah. Okay, thank you.
Very easy. Okay. Other questions? All right. If not, let's dive in. So the first thing you do is you write a recipe file, and you can compare that. If you're familiar with Docker, you can just compare that to the Docker file. It's the same thing. It's the recipe in order to build the Singularity image. So basically, you specify the base image for the operating system. So in this case, it would be a focal Linux, which is basically Linux Ubuntu 20.20, 20.04, and you specify the mirror URL, so basically where the operating system image can be found. So that's quite easy. You can do other distributions. It need not be Ubuntu. You can do any which you want, which can be done with Docker. Here's an example for CentOS. So basically, here the bootstrapper is not the bootstrap, but rather Yum, which is the package manager for CentOS. You specify the version, in this case 7, and you specify again the mirror URL. So it's very easy to get as a base image whatever distribution you like. A very popular distribution is also Alpine, and the advantage of that is that it is really, really small. So if you want smaller images, then Alpine is definitely a good way to go. Ubuntu and CentOS tend to give you larger images. Let's say a base image would be somewhere between 250 and 300 megabytes, while a base Alpine image is something like 50 megabytes, so it's a lot smaller. Okay, so you can also bootstrap from Docker. So if you have a Docker image that is that is useful to you as a base to start your own image with, then you can just bootstrap from Docker and you specify the entry in Docker IO. So here we would have a Debian, so the Jesse version of that. I don't remember which one that is exactly, but basically this shows that you can just use Docker as a base image, and then you can add stuff to it. So that's also pretty neat. And this, of course, also immediately remedies the fact that it's a different compiler system. Yeah, indeed, it's not Docker, but still you can get your Docker images to run, your Docker files to run just using a Bootstrap Docker. Okay. Yeah.
Jan, I have a question. Is
Cool.
it possible to use a Docker image from local repository, or it should always
Um,
be in the Docker Hub itself?
Typically, I do it from Docker Hub. I would have to look whether you can do it from a local thing. The reason why I don't know is that I typically don't write Docker files. We'll come
Yeah,
back to
okay,
that
I
later.
see.
But there
Yeah,
is a
okay,
very
thank
nice
you.
way of getting the best of both worlds. So that's
Okay,
why I don't write Docker files. But
yeah, okay,
via Docker IO, it's always possible. That's no problem.
yeah, okay.
So you can use any public Docker container or even a private Docker container if you log in. Okay. So then, of course, you need to get a token, specify the token, and that also works. No problem. Okay. Then there are sections in the Singularity recipe, and one of the first section is, of course, the setup, and that will be executed on host. So, for instance, here the uh, directory is created in the container using this um, environment variable. So basically, in the root system of the container, we're going to create a sample data directory. And so basically, the host has access to the file system, which is going to be created for the container, for the image. Then you can copy files, and that's with the files directive. so the file section in your recipe file. And the semantics of copying is like the copy command. So basically on the left, you have the file to copy. On the right, you have the destination to copy to. And you can use wildcards, as you can see, and so on. So left is the host file system, right is the image file system. So all of this is done by the host operating system. Okay, setup section, file section. Of course, if you need a directory to copy to, you first have to create it in the setup section of your recipe file. That's fairly obvious. Okay, so the next thing is post. So the post phase actually is that is past the bootstrap phase. So basically, when the post phase starts, you are sure that your base operating system has been installed. So that means that all operating system commands which you have at your disposal in the distribution you're using are available. Also, of course, package managers, and that's what you typically do in a post phase. You're installing your software which you need. So you use apt or yum or whatever package manager in order to install software. But of course, you can also just download some source distribution, a tar file or whatever, and then you can do the typical configure, make, install cycle of software installation. That's no problem. Then all of that goes into the post section. So here's an example for Ubuntu. So the first thing that happens here is that you include the universe section in the source list for Ubuntu repositories, if you need that. You do an apt-get update and an apt-get install, in this case for an application which is called Grace. Don't forget the -y, because that means otherwise apt-get is going to ask for confirmation, and you don't want to have to give confirmation when you run your recipe. It should run unattended, so that's why the -y is there. Yum has a similar flag in order to run silent, well, not silently, but run without asking for feedback. So here's the example, it's also -y. Okay, so that allows you to install any software easily. And of course, the nice thing is that it will take care of the whole dependency chain. For instance, if you would want to get Grace to run on an HPC system, you would not really make system administrators happy, because that really relies on a very old windowing toolkit, which is called Motive. And to get that to install on a modern HPC system is very unpleasant. While if you can just do apt-get install, it's done automatically, and all the dependencies, all the awful old, archaeologically very interesting software, it just gets pulled in and it works. Okay, so the post section is where the payload usually goes. I mean, this is where you really install the software which you need in your repository, in your image. Okay, some other sections which are interesting, for instance, the environment section. So that just allows you to define environment variables, which will be available in your image when you run it. So it's just very easy. You just assign values to the variable in that particular section. Also useful is run script, and that is actually the action which happens if you just run your container without any arguments. So you just specify a line which says which application to run. So in this particular case, because this is a running example, if you would just Singularity run this container, or this image rather, then Grace would be executed. By the way, for those who don't know, Grace is a plotting program, so it allows you to plot data. Okay, You can actually have multiple applications within a single Singularity container, but for that I would just refer you to the documentation, which is actually quite good. And yeah, it would just take up a lot of space here to replicate what is actually very nicely explained in the documentation. But basically, you get the gist. The Singularity recipe file really describes your data, your container. Some other things which may be useful is some testing and some meta information. So you can test the container by executing Singularity test with the image. And what is done is whatever is specified in the test section of your recipe. So in this case, it would just check whether Grace runs by showing the version of it. But of course, you can make this very elaborate. You can do actual unit testing here if you are developing software. You can do other kinds of tests. So this can be very useful just to check the sanity of your Singularity image. Okay, so with respect to meta information, you can add labels. And there are a few standard labels like maintainer, like version, and so on. So this just allows you, if you distribute your container, to add some information which might be useful for other users. And you can get to that with the Singularity inspect command and again your image. And you can even provide help. So if you have a help section, then whatever is there will be displayed when you do Singularity help with your image. So again, that helps a little bit with respect to um, distributing your Singularity containers, having them used by other people. Okay, so all of this put together gives you something like this. Of course, I have left out things. Typically, when you see the triple dots, some stuff has been left out just because there's not enough space on the slide. But basically, you see how it works. You have the bootstrap thing, and then you have several sections. So you will typically have a post section, maybe a run script, maybe a test, but definitely a post section. The files and um, the, the first one, which I forgot the name now, those will go here, the setup. So first setup, then files, then post, etc., etc. Okay, so any software installation happens in the post phase. That's important to remember. Okay, now how do you build an image? So that's when you build an image, it creates an image first, so that's the file. Then it will install the base OS, and then the software which is specified in post. And you can do the build with Singularity build, the name of the image, and the name of the recipe file. And you have to do that with sudo. Okay. When you change a definition file, typically only modified parts are executed. So if you leave the bootstrap alone and you only change the post part, then the software installation will be redone, but not the bootstrapping. So that's kind of nice to do updates, upgrades, or security fixes and things like that. Okay, so there are different types of images. So the default is a SIF file. So that's a Singularity image file. That's what SIF stands for. And that is totally standalone. So you can FTP that to, or secure copy that to some host. If Singularity is installed, you just run your image. Very easy. You can also have a squashfs image, which is compressed and which is read-only, can sometimes be useful. You can have a writable, so that would be an X3 file system. And this can be sometimes useful to experiment, so that basically that you can modify a running image can be useful. You can also use a sandbox, which is just a directory. And again, that is very useful for experimenting and to get your image right. This can be convenient. So properties of images, typically images are read-only. That means that if you need to write data, which you probably do want to, because otherwise what's the point, then actually you do that on the host file system, which can be overlaid on your image. So basically it can be accessed from your image if you specify the right flags when you run the system, when you run the image. If you have pseudo writes, you can do read write. Again, that's okay for experimentation. But yeah, I would, as best practice, we'll come back to that as well. But as best practice, I would not advise to build your image in a read write mode. I'd always suggest that you have a recipe file which you can run and which will generate your image without intervention, without you having to type something on the command line to modify the image post creation, because otherwise things are not reproducible easily. Then you would have to provide instructions on what to do in read write mode after you've bootstrapped your image. And yeah, that's not going to be a good way of working, but okay. So if you want to do that anyway, you can just mount an image. And of course, again, you need pseudo writes for that. You specify writable, and then you can actually modify the file system in that particular image. Okay. As I said, don't do this to get your final image because you will regret it at some point because things are not reproducible. So they will be mounted in this particular directory. Okay, so to just inspect what is in your image, you can just do Singularity mount and it will be mounted same location, but now you can just look around at it, you can't modify it. Okay, so you can do a remote build. So that can be useful if for whatever reason you can't build on your local system, then in fact you can do a remote build, but this requires an account at scilabs.io. You specify the recipe file, you click a build button and the image is produced, and then later on you can just retrieve that image from the Scilabs.io site. So it's just all in the cloud. You don't need any software installed, just a web browser. And you, of course, you are required to create your Singularity definition file. That is pretty obvious. You can build it on the command line. So you can do a remote build by just doing Singularity build remote. Then you get your image and the definition file which you specify. So that means that your image gets, your recipe file gets uploaded to Scilabs.io. The build is done there, and the resulting image is downloaded from that site. Experiences are, in general, positive. There is one image which I, for totally unknown reasons, never ever got built on Scilabs. I've never been able to figure out why, but mostly it works quite well. So you would need a token in order to do the remote build, and this you can just create on Scilabs.io if you have an account. You just create a token and you install it into a .singularity directory in your home directory, just as Scilabs token, and you just paste the token in that file. It's just a text file, nothing more. And from then on, you can do remote builds. Okay. So that basically means that you don't need pseudo writes on the system where you're, well, where you're going to. I hesitate to use the word build because you're not going to do a local build. You're going to do a remote build. But where you execute this command, you don't need pseudo writes. So that's a good thing. Okay. There are some other options. So there's Singularity Hub, as I mentioned. You can use Docker. for the base image and so on. You can also use local container, archive, etc., etc. So there are many ways to actually build a container. Okay, any questions at this point? All right. So one of the things which I already mentioned is that I typically don't write Docker files. And the reason for that is that there is a very nice tool which is called HPC CM. It's written in Python, and the name is derived from HPC Container Maker. And it's a tool which is developed by NVIDIA. And of course, they are quite interested in that kind of thing because they have quite a lot of containers which you can use for deploying GPU software. So most things which they have as software, they make available as containers. So that's actually a very nice thing. And of course, they realize that they can't get away with just Docker. They also need to support other formats, and specifically, they realize that in HPC, where they have a big market, they need to support Singularity. So this is a very nice tool. And the thing is, you write a Python script that defines the container. It's not a standalone Python script. It's actually just a bunch of HPCM functions which you execute, but those define your container. And that is nice because it can actually be translated into either a Docker file or a Singularity file or even a bash install script. The bash install scripting is restricted to anything that uses opt. So it's just for Debian-based distributions at this point. So that's a bit a pity, but yeah, okay, I can live with it because mostly I'm using HPCCM anyway to generate either a Docker file or a Singularity recipe. So the nice thing is you don't need to learn the specifics of either Docker or Singularity in order to create containers. And also you create one definition file in the HPCCM and you get both. Yeah, question.
Um, can we somehow use this tool to convert Docker file into Singularity recipe, or that's not possible?
Not really. No, it doesn't read Docker files. But of course, what you can do is
Yeah,
use the Docker file which you are interested in as the
yeah,
bootstrap. And then, of course, the Singularity, sorry, what's it called? The HPCCM
yeah,
specification thing, the definition, is in fact just the definition for either Docker files or Singularity recipes.
yeah. Okay, I see. So we can actually
So,
write a basic Singularity recipe and use
yes,
Docker file as a bootstrap to
exactly.
that.
Yes, exactly.
Yeah.
That's
Okay.
the easiest way to deal with that.
Yeah. Okay. Thank you.
So the advantage is you get a high-level description of your container, and you compile that down to a specific recipe, either a Docker file or a Singularity recipe. So I rather like that approach. Okay, so this is an example of an HPCCM recipe. Um, so it's a Python script, so you can use any Python library which you might need. In this case, it's in part for the sake of the argument, but I'm importing Patlib, which allows me to do file system stuff in Python. Okay, so the first thing to do is to choose a base image. And you specify that just by using the base image function. And you call that on stage 0. So stage 0 is the creation of your image. And this one is based on Ubuntu 2020. So note that this is in fact a Docker file. So this is a Docker specification. This one will be obtained from Docker.io. Okay, and once you have your base image specified, you start by adding things to the stage. So in this case, um, the sorry, HPCCM has a lot of primitives, and one of them is apt-get, which which basically means that you are installing packages. And okay, it's called apt-get, so basically it will do the Debian thing. So in this case, we specify operating system packages, and what we want is build essentials and make. And also we want CMake. And as you can see, for CMake, there is a special built-in specific for CMake, because CMake is software, and you have to, for which you have to agree to an end-user license agreement. And typically, when you install CMake, it will prompt you at some point, yeah, okay, do you agree to the license? Please first read the license, then agree to it. But there is a command line option to do that silently. And the CMake function will just take care of that. You just specify that you agree to the license agreement, and it will do everything silently. So that's nice. There is also a lot of software which is in fact which has its own primitives. So for instance, if you want to install the GNU compilers, you can just use this primitive here, just GNU, and then it will actually do the installation of the compilers. You could do it using apt-get. You can also do it using GNU. The nice thing is that it's then also aware of the GNU compilers. The stage is aware of the GNU compilers, and it's easier to use later on. You have similar things, for instance, for MPI, but I'll come back to that later. If you do that, then it will actually build the MPI library, which may or may not be what you want. I'll come back to that later. I'm just mentioning it that it's there. And then, of course, it's a Python script. So here, this is just a Python statement. I'm using pathlib in order to actually specify a source directory on the local file system. So that's, of course, on the host file system. We have an example directory. It's just a Python variable. And then for each file in the source directory, I'm going to copy that into my stage 0 image. And basically, this is just a Python statement. I'm using an f-string here to make things happen. And you can specify that if you copy something into a directory and that directory does not exist, you can simply create it if you set underscore make dir to true. Okay, so as you can see, this is quite high level. I don't need to know the details of Docker or Singularity. I can just compile it down to whatever I want. Okay, so how do I get my Singularity or Docker file? Very easy. I just run HPC with the recipe specified. That's just a Python file which we created, and then you specify the format. So either Singularity or Docker or Bash, and it will print to standard output. So you redirect it to some file. And very similar for a Docker file. The only thing which you change is the format to Docker, and of course you redirect to Docker file. So really, really easy. And what I like about it is that sometimes it's nice to work on your own machine with Docker rather than Singularity, or you start out with Docker. So it's nice if I use HPCCM, I just specify the Python recipe, and I can use either Docker or Singularity, whatever I want. Okay, any questions at this point? All right, so now we know how to build containers. So now it's time to run them. Okay, so to execute the run script, remember we had the run script thing in our Singularity recipe. So if we just want to execute that, we can do Singularity run and then just the name of the image. So in this case, grace.sif. So this would actually just start an X11 application well, a motive application on the local system. So we would get a graphical user interface for the Grace plotting program. Okay, but as I already mentioned, an image is read-only. So you can't do anything in the file system of the image itself. So that's annoying. Well, it's not annoying, it's just how things are. And of course, also you probably need access to some directories. And typically when you just Singularity run something, you have access to the current working directory, but not necessarily to other directories on your file system. So you need a way to expose other directories. So what is bound by default is your home directory and the current working directory, and also things like /tmp and /vartmp. So those are um, automatically available in your image. Okay, so if you want to execute an arbitrary command, then you just use Singularity exec, the name of your image, and then the command which you want to execute. So in this case, there is also a Grace bot executable, which comes with Grace, and essentially that just allows you to create plots without human interference. So basically, it will just take data. It will take what is called a batch file, and that contains a description of your plot, and it will produce that. Okay, just an aside, I'm absolutely not promoting Grace here, because Grace is really an old application. As far as I know, the last update to it has been in 2005. So please don't start using it. It's just a very good use case because getting it installed on HPC systems is bloody hopeless, while with Singularity, it's just very easy to get done. So that's why it's running example. Again, I'm absolutely not promoting Grace, absolutely not. Okay, so this would start the X11 user interface and so on. All right. So how do you integrate it into a job file? Because that's, of course, also pretty important. This is a typical PBS file. You have your shebang, you have your PBS directives, nothing special. We change directory to the directory where the image was, where the job was submitted, and then you just run Singularity exec with whatever command you want to execute in that image. So it's really straightforward. Singularity is part of the system images, so you don't have to load any modules. It's just available on all login nodes and compute nodes. Okay, so you can use Singularity image in any workflow. So you can even have a PBS script that contains multiple calls to Singularity images. That is possible. Whether that's a good idea or not depends on the granularity, because of course, starting an image takes overhead. So if you have a for loop here, which does something that takes half a second, and you do that a million times, and each time you start a Singularity image, you're probably not going to be happy because that's not going to be efficient. So be a little bit careful what you do with your workflows, bearing in mind that starting a container obviously generates some overhead. Okay. A nice thing, and especially to execute stuff or even for development, is that you can actually run your Singularity image in interactive mode, so as a shell. And that's quite nice because, for instance, you can create an image that has all the tools which you need in order to do your software development. All the libraries installed, all the testing tools installed, the build tools, etc., etc. And that gives you a portable development environment. And that is something that is very actively being promoted nowadays. For instance, you see that there is a project which is called Toolbox, I'll put it in the chat because it's less obvious than you might think. It's pronounced toolbox, but it's tool BX. So this is kind of interesting because it actually allows you to create containers, and the intent is to do development. Yeah, I'm a bit in two minds about it because it requires fiddling. Well, no, it doesn't require fiddling. It encourages fiddling in the sense that you can actually you can run it and you can install software in it on the fly, which is kind of nice, but also very dangerous because typically that does not give you reproducibility. So unless you're careful, you're not able to share these images. And doing development in an image that's not shared is, in my opinion, not really a good idea. So I'm very much in two minds about it. Okay, so one of the things you have to be a little bit careful with when you run Singularity shell is that it will default to bin shell, not to bin bash. So be a bit careful there. Also, be careful because your home directory will be mounted in the image, and that means that if you run a bash shell, it will actually use your bash profile or your .bash rc, and that might contain stuff which is not available in the container, and you might get some errors. So just try and write a portable and a safe bash profile, bash rc, with some if statements and so on to avoid nasty surprises. So it's nice to test software. It's also nice to do development, as I mentioned, but yeah, it's not necessarily very reproducible. Okay, so the current working directory you have available when the image is executed. So that's easy. That's bound automatically. It's using overlays, so that works. Your home directory as well. So that would be the home directory of the user in your container. Okay, additional bindings. So you can use a -b flag, and then you specify host path and image mount point. So for instance, you would do something like, okay, I have a local directory, well, a directory in my home directory, which is called data. So this is the host directory. And I want that to be available in my image. And I can mount it, for instance, in the MNT data directory. So back in the old days, but that depends on the version of the kernel on the host system you're running on. Back in the old days, the overlays were not available, and you would have to make sure that if you wanted a mount point in your image, that the directory existed. So basically, in your recipe, that would mean in the setup phase that you would have to create those directories. Nowadays, overlays work. I have not seen any problems with them anymore. So basically, you can actually just if it doesn't exist, it will be created. And also, if you want directory to be present with the same path as on the host system, you can just specify -b and data analysis, for instance. So the data analysis directory will be available at that same mount point in your image. And you can have multiple -b flags. So you can mount as many directories as you require in your image. And this is at runtime. So that means that you can have a Singularity image that one day you run with a binding to a certain directory and the other day to a different directory. So this is typically the way which you deal with data, which you require as input data, or where you want to write your output data, you just mount those you bind those directories using the -b flag. Okay, any questions about this? Okay. So of course this is HPC. So we're interested in not just in running just single-threaded applications, but rather we are interested in running multi-threaded applications, and we're also interested in MPI. Okay, so let's start with multi-threaded applications. Actually, it's fairly straightforward. So here again is another example of a recipe file. So it's based on a somewhat older version of Ubuntu, this decennial version. I think that's the 1804, if memory serves. And again, we just use the base image from the Ubuntu distribution. No problem. We have post. So we, yeah, it's always a good thing to do an apt update before you do an install. Also note that normally if you install something on a Linux system, you would have to do sudo apt-get, etc., etc. The post commands are in fact running as root, so that means you don't have to bother with you don't have to bother at all with sudo because it's run as root anyway. Okay, so we install the build essentials. We also install a git in our image, and then we go to cd temp. As you can see, this is basically just a bash script. And then I do a git clone of a certain repository. I go into the new repository to a certain directory, and I can do a make clean of the applications which are in there. And in this case, that would be an OpenMP application, so a multi-threaded application, which is just built by the make file, which is included in the directory. Okay, and then I can move the executable to the bin directory. And notice that I do something which in practice, well, which on your own system you would never do. I mean, this is weird. My own executable is being copied into the user bin directory, which is the system directory. I mean, no sane person would do that on his own Linux system. I mean, you would maybe copy it into user local bin or something, but never to user bin. So, of course, in containers, that's not a problem, because the easier you make it, the better. And as long as you don't override something which happens to be in that user bin directory, it's no problem. And the advantage is that, of course, you don't have to fuss with paths. Everything will be there. So also, if you have a make install, which for this particular make file there is no make install, but otherwise you could just do a make install, and it would just take the defaults. It would install in user bin, it would install in whatever etc or user lib or whatever. It's fine. There's no problem with that because it's your image anyway, and the easier you make it with respect to paths, the easier your life. So there's no problem at all with that. What is definitely a good idea if you create your own images and you build things, it's to clean up. Because, of course, if you don't clean up in this phase, the whole build directory will be there. All the build artifacts will be part of your image. And in this particular case, this real-life repository, it's pretty big. If you clone it, you will end up with something like near to 150, somewhere between 150 and 200 megabytes. So you really don't want that in your image. So afterwards you clean up, and here I just remove the entire repository, which I just cloned. So that's no problem, and that's actually best practice. Both installing into system directories and removing all build artifacts is definitely good practice. Okay, so that gives me an OpenMP application. Of course, this also happily works with pthreads and so on, it doesn't matter. But of course, this is HPC, so I'm giving an example with OpenMP. Okay, so this is a job script that would run this, and it would do, in this particular case, a scaling test. So it will check how the performance evolves with respect to the number of threads which is used in the application. Okay, so as you can see, nothing special happens here. I'm asking for a node with 28 cores. So basically, this is an example that originally ran on Brainiac in tier 1. But of course, adapt for the number of cores which you're using, which would on Genius be 36, of course. Okay, and then I have a for loop over some number of threads in order to do my scaling test. And I just export OMP num threads. I set it to the number of threads for this particular iteration in the loop. And this is used by the Singularity image to do the testing. And here we have the normal thing. So we have Singularity exec of the image, which I just created. Okay, I don't know why this is OpenMPI, because that's a very stupid name, but okay, never mind. And then I just run my OpenMP application with any arguments which I want to provide. Okay, so the environment variable OMP num threads is actually taken from the host when the Singularity container is run. So it's very easy to control your OpenMP application from the host when you run the image. Okay, so one of the things which is interesting to note is that, of course, the compiler version in the image does not need to be the same as is available on the host. For instance, although I would not advise it, what we did right now was create an image that actually uses the GNU compilers. And often it's worth trying whether the Intel compilers give you better performance for OpenMP. But this means that actually you can use, for instance, Intel compilers to create your image and then run it on a system that does not have Intel compilers. The runtime libraries will be part of the image, and you can just execute the OpenMP Intel application on a system that does not have any Intel libraries installed, because they're part of the image. This does not pose license issues, since licensing is based on using the compilers, not on using applications. Okay. Any questions about this? Okay. One of the things which is important is performance, and we'll discuss that later on. All right. Maybe this is a good time to have a short break. So let's say something like 5 minutes, perhaps, to grab a cup of something, coffee, tea, whatever. So I'll put a note on the whiteboard. Okay, can I wipe this thing easily? Here. Okay. They have improved the whiteboard. I'm still not used to it because it's the first time I use it this academic year. Okay, let's have a break. And let's make that 10, 10. All right. Meanwhile, if there are any questions, feel free to type them in the chat. I'll also grab a cup of tea, so I'll be back in a few minutes. But I'll keep an eye on the chat when I return. Okay, let's continue. So there are a few interesting questions in the chat, and I'll answer those in a second. I'm first going to reshare my screen. Just a second. Here it is. Okay, because otherwise I forget that and I start talking about slides and nobody sees it. Anyway, all right. So let's address the questions. So the first one is fake root. That depends. So you can use it to build images on systems without having escalated privileges, but only if those systems are configured correctly. The problem is that something needs to be done in etc sub IDs, if memory serves, and subgroup IDs. So you have to set ranges of user IDs and group IDs, which are used in the container. The default of those typically means that Singularity fake root does not work. So if it does not work, you would have to bother your friendly HPC system administrator to make it work. So normally on Genius it should work. I'm not sure about Brainiac, and I have no idea about other VSC sites. So in theory it can work, but not always. And that's the problem. With respect to recording the session, yes, it's being recorded. The problem with making it available is that I can't really make it public. What I can do is send you a private link to it, so that you can review the session. If you need that, just drop me an email, then I'll send it. I can't make it public. I'll explain why I can't make it public. Basically because your names are visible in the chat, and that's part of the recording. So that means that I can't really distribute this without having your written permission due to GDPR stuff and so on. So that's stupid, but that's how it is. Okay, and then there is a question from Florian. Is it possible to the image file? Something. Okay, so reverse engineering. I think that's what you mean. So you have an image, but you don't have the original Singularity file, but you would like that. And basically, can it be extracted from the image? Not that I'm aware of. I've never seen that done. So yeah, you would have to look for it. I don't know. My guess is that the answer is no, but I'm not sure. The reason why I would suspect it's not the case is that I can think of use cases where I really wouldn't want that. So for instance, suppose I'm a commercial vendor and part of my installation is having the source code of my application as part of my image. Of course, I don't want to distribute the source code, so I would, in a later stage, I would remove it, but that would still leave information about the build process and so on, which I might not want to share. So I don't think so. If I were writing Singularity, I would make sure that you couldn't. Okay. Any more questions? All right, so things get even more interesting when we do distributed applications. And of course, distributed applications in the context of HPC means MPI, typically. That's still the mainstay of doing distributed applications. So then things get interesting because basically, how do you deal with MPI? Of course, it's very easy. I mean, you just opt install MPI and you're done, and pitch or open MPI or whatever. But if you do that, you would notice that your performance is not necessarily very good. The reason for that is, of course, that on HPC systems, well, first we use InfiniBand, as a interconnect between the nodes. So if you have an MPI version, an MPI implementation, an MPI installation, which is not taking advantage of InfiniBand, the performance is going to suffer quite a lot. So, okay, yeah, well, so what's the problem? You just install InfiniBand at your then. Yes, that's true. But then again, there is still some tuning, which basically happens on the system and which allows you to get a little bit better performance. So if you want to do that, then one of the things which is definitely a very good idea is to ensure that the version of MPI which you have in your image is the same as the one which you want to run with on the host system. So those should be the same. At least the same family. I'll come back to that later on. So here we have an example where we actually install a lot of stuff for InfiniBand. So basically these here, the lib MLX, these are the InfiniBand driver libraries. And we also install InfiniBand verbs, which is also an important library because the MPI implementations typically use IB verbs under the hood. And then we have, in this particular case, we install OpenMPI as MPI library, and also the binaries and so on, all the packages we require. Again, the build essentials and Git. So if you do this in using HPC CM, you could just do stage 0 dot, and I think it's MPI then, and it will install OpenMPI. So basically here, we are relying on whatever is in the repositories for this particular distribution, which is again an Ubuntu-based system. Okay, we use the same thing for installing our own software. So it pulls from a repository, clones a repository, and it is going to build an MPI application in this particular case. And again, we clean up. So same thing as for OpenMP. That's all there is to it. Okay, so I already mentioned this. And then we have the PBS job script. So again, the usual stuff, shebang, PBS directives, blah, 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 nothing interesting. We move to the submission directory and we load a module which contains the same OpenMPI version as we just installed in our images. So this example is pretty ancient. I mean, 2016A is quite a while ago. It's still available on tier 1, where again, I apparently did these experiments because of the PPN is 28. And then you do MPI run and Singularity exec the name of the image and the command. So we're doing something hybrid here. So we are using the host side MPI implementation in order to do the process management. So the MPI run ensures that processes will be started on all the hosts which are involved in the job, and on each of the processes we specify, and that's the job of the host MPI implementation. And that's of course why it's important that the host implementation and the image implementation are the same, because the host implementation is going to provide the environment in which the processes run. And of course, the implementation in the image will use the infrastructure which is provided, and that's only compatible with a similar MPI implementation. Hence, we have OpenMP on the host, OpenMPI on the host in order to do the scaffolding. And we have the MPI libraries, the corresponding MPI libraries in the executables, which run in each of the processes which are doing our parallel application. Okay, then there's one additional thing which needs to be mentioned, and that's this MCA parameter. So basically, if you just run OpenMPI, it's going to create a temporary directory somewhere where the image doesn't have write permission. And that is very annoying. The easiest way to get around this is to simply say that the ortitender base, so basically the temporary directory which OpenMPI is going to use, is just going to be /tmp. And remember, /tmp is being mounted into the image from the host. So that's your simplest way of dealing with it. Okay. So I already mentioned that. So it's best to have the same version. All right. So any questions about MPI? So typically you would want to build your applications either with OpenMPI or even with Intel MPI. You can do that because nowadays Intel is much more liberal with respect to its software licenses, and anything one API you can actually just use as long as it's not for commercial purposes. So it's quite a lot more liberal than they used to be because Intel licenses required a couple of PhDs to understand, and even Intel employees didn't understand their own licensing model. So now they have simplified things, probably because they, well, really got tired of trying to explain something and not knowing how it worked. Okay, question? Is there a question?
Yes, I have a small question. So
Okay.
if you would be using the Intel compilers, which are
Mhm.
installed on the cluster, then
Mhm.
you just mount the directory where the Intel compilers are installed in the image, or how would you do it?
You could do that. Yes, you could do that. No problem.
Okay. Okay.
So basically, and especially since we have the module system on the clusters, it's rather easy. You just have to mount the you simply have to mount the directory in the software stack, and you've everything available. Of course, you have to make sure that the environment variables are set appropriately, but typically, if you do a module load, it's fine. And of course, if you use overlays, so if you don't use a different mount point in your image than you do in on the host, then of course even the module system will work because that just modifies environment variables. The environment variables are used. So if the paths are the same, which they will be if you use overlays, it's really very transparent. So that should work quite well.
Okay, thanks.
Okay, so this is one approach to MPI. I don't have a slide about that, but I should mention it. So this is one approach to MPI. You have the MPI software installed in the image. The version is the same as on the host. So this is a hybrid approach. You could also take a different approach. You could also say, well, okay, I'm going to build my software in the container, and what I'm going to do is, in fact, I'm going to mount the relevant directories with the libraries in my image. So basically, I ensure that the link paths are okay, so that the link has been done with the same paths as on the host system. I use overlays again in order to mount the MPI distribution directory. So basically, the image does not contain the MPI implementation. The image mounts the implementation from the host system. So that's another approach, which is also quite useful. Of course, the building thing then gets a bit more, maybe a little bit more challenging. And of course, you also will lose portability because you really rely on the mount points. You can get around that by just saying, well, okay, I'm not going to use the same path in my image as in the environment. I'm going to use I'm just inventing something. So opt MPI as a mount point for the distribution. And that gives me a level of portability, because then I can run my image with a dash B, capital B, and use the mount point to mount the distribution of MPI which I want on a fixed point, which would make the linker happy, the loader happy when you run your application. So that's another way to do things. Yeah, I don't know what's mostly done. Back in the old days, we used the hybrid approach. At the moment, I don't know what users are typically doing. Okay. So that's with respect to MPI and distributed applications. Another topic that is really interesting when you think about containers is services. And services, of course, is a very broad term, but the typical application would be something like, okay, I have this, and yeah, that typically comes from bioinformatics. I have this application that actually requires that somewhere a database is running. For instance, a PostgreSQL or a MariaDB or something like that. And yeah, there is no database. How do I do that in my job? I can start a database, but then the database has to be installed on the system, and yeah, okay, it's messy. Can be done. It's not as if it's impossible, but it's yeah, not so pleasant. So what you can do, of course, is to pack your database into a container, into an image, and run it as a service. So in this case, the image runs services, and that can be, for instance, also a web server if you want. It could be a relational database system, as I already mentioned, PostgreSQL, MariaDB, whatever, other database systems, MongoDB, which is not relational, but anything you want, basically. Okay, but of course, that means that you start processes, but those processes also need to be cleaned up. For instance, I would prefer that if I'm running a database, that the database is shut down properly. If it's not shut down, I might end up with a corrupt database, which is not what I want. So that's important, and that's where services come into play. Also, for certain workflows, it can be quite convenient. So the workflow is start a service, then do client interaction, which is just part of your job script. And then at the end of the day, you stop the services. That's your typical workflow here. So all of this you can do with Singularity instances. So for instance, the service can be running in a Singularity container, in a Singularity image, and your clients can be different images. No problem. So this would be an example to define a service. And this is something that if you are familiar with Linux on a somewhat deeper administrative level, that you might be aware of. So this is basically defining a service. So that is just a shell script, nothing more. It defines some environment variables, and in this case, it's for an Alpino server. So Alpino is a server application that gives you natural language processing services. So actually what it does is you provide a text and it will do part of speech tagging. So it's going to analyze the text and it's going to tell you which words are nouns, which words are verbs, etc., etc. That kind of analysis. And you can run that as a service rather than as an application. And for this particular user, this is a real use case. So for this particular user, that made more sense than each time running an application on a small text. Okay, so what you do when you have when you define a service is that typically you define the states of your server, and the states can be start, stop. There may be others like restart, I think, and so on, but typically for our purposes, start and stop is fine. And this will be run, the script will be run by the system. Okay, so for start, that means we are setting up the server. So we define a port, and this is one of the places where you already may have an interesting issue. So you require a port on the system. That already means that that port must be larger than 1000, because all ports with number 1000 are only for root users, for users with escalated privileges. So that's one thing. Another thing is, if you run multiple jobs on the same node, and each of them starts such a service, then of course you have to be quite careful, because if they pick the same port number, that will work for the first service, and then the next service that starts in a different image, in a different job, will tell you that that port is in use, and it will basically crash. Okay, so another thing is, of course, that if you run a service, or if you use a port, it also might be that another user on the same node is also using that same port. So one of the things that you definitely should not do is use the default ports of whatever application you're using. So for instance, suppose you run a web server, please don't use port 8080 because everyone will be using port 8080. I mean, that's not a good idea. So if you have just a single job and you need a port number, just use your VSC number because it's very convenient. It is something like 34567, and basically that is unique for you by construction. Okay, if you need multiple ports, you have to be a bit more creative. But basically, if you use something, let's say, in a range in the neighborhood of your VSC number, it's probably fine because the probability that another user will, with a number in that range, will end up on a node on the same node and use a port is fairly limited. So that's an easy way around that. But it also means, of course, that you have to have some way when you start your service to specify a unique port number. And one way to do that is to say, well, okay, I'm going to use a configuration file, and that is going to be in the directory conf port number. And this directory is going to be an overlay. So it's going to be taken from the host image, and for each of the services which starts, there will be an individual directory with a port number file in it. So that it's really unique across each of the instances of the services which are running in different jobs on the same node. So that's a way to get around that. And then you launch your server, check the documentation of whatever service you're using. In this case, starting an Alpino server is fairly straightforward. You need a lot of stuff here, which for the life of me, I have no idea what it does. But the important one here, of course, is server port. So basically, I'm specifying the server port here, which is the environment variable which I got from that configuration file. Apart from that, I don't think there's anything interesting here. Of course, one of the things which you would like to check is where your output goes. So basically, in this case, we just okay. Here's something strange. I don't think that that is okay. I would have to check the script. I don't remember why this is here, but okay. Anyway, if you want log information, then of course redirect the output to files where you log your data. But again, remember that if you specify a file name here, it should be unique for every instance of this service. So you can, for instance, base that on the job number, or for instance on the port number. That would be another option. And of course, similar. This is for standard output. This is for standard error. Okay. This part I really don't remember. It's probably something very specific for Alpino. Probably it's able to read some stuff when it starts, and if you specify def null, it doesn't read or something like that. I don't remember, but it's not really relevant. Okay, so this is all that happens when you start a service. When you stop the service, well, in case of Alpino, nobody cares because you don't have to do anything. It will just be killed. That's fine. But normally for, let's say, a relational database or something, you put a command here to shut down that database properly. That's the idea. Okay, so this you have to define. This also has to be part of your image. So that goes into your image. And now you can, in the image, you can start a service just by service Alpino start, service Alpino stop. So this is just, this would work on Ubuntu. You may have base images that use system control rather than service, and in that case, it's just a corresponding system control statement. Okay, so now we can have the recipe. So we have to make sure that that Alpino script here, so this guy, goes into etc init, because that's where that kind of service definitions lives. And in post, of course, we have to modify the permissions for that thing so that it's actually executable. That's important. And we also have to create the directory, the conf directory. Well, we don't have to anymore with overlays, but it's always safer to have the mount point already. Okay, and then the start script would just be service Alpino start. So the start script section, that is specific for services. And of course, you also have a corresponding stop script section. And this allows you to create an image that you can run as a service. All right, so how do we run an instance? So we have Singularity, but we have instance start. And this just specifies the name of the image. And then we have Alpino01, which is probably the name or something. I don't remember why this is here, to be honest. I would have to look at the exact scripts. But the important thing here is basically that we bind a host directory to the conf directory. So we have a conf01 directory, a conf02 directory, etc., etc. And this is intended. Yes, this is the name of the service. Sorry, the name of the service is Alpine01. That's the point. But basically, for each service that we start, we can have a unique conf directory and, of course, a unique service name. Okay, so that will start the instance. And yeah, that's the instance name. Now I remember. Okay, so how do you interact with the instance? Well, you can list all the running instances just by Singularity instance list. And if you have only one instance running, there will be one. If you have multiple instances, you will have multiple. And of course, you can mix. I mean, in this particular use case, you would have multiple instances of the same service. But of course, you could have multiple services as instances. So for instance, there are some applications that require both a PostgreSQL database, but also a MongoDB, and perhaps a web server. So you would create start files, well, you would create service files for each of those services, and then you can start the instance of the PostgreSQL database, and then the instance of the MongoDB database, and then the instance of the web server, etc., etc. So instances need not be the same thing. Okay, and to stop it is very easy. You just specify Singularity instance stop with the name of the instance. Okay. All right. So perhaps I can show you, because this is just starting and stopping, but maybe it's better that I show you the real thing. Because then you also see what the actual PBS script looks like. So that would be here. I'll increase the font size in a minute. This is just the service script which you have seen. There is nothing more to it. There is an additional case here. Start, stop, why is that there? I don't quite remember. But this is the entire, yeah, okay, I defined it as functions. That's the point. I defined two functions, one for start, one for stop, and then the case statement just executes those functions. It's a bit cleaner. Okay, whatever. The more interesting thing is the PBS script. Let me go to raw and let's increase the font size a bit. Otherwise, there is no way you can read this. So this is just a standard PBS script. So we have the shebang, we have the PBS directives, no problem. Change the working directory and so on. Okay, so we check whether an input file is given. That input file is given via the -v option of qsub in this particular case. Okay, okay, so this is basically because this was intended as a worker job, and I do something in order to ensure that things work. If it's not run as a worker job, okay, forget it, it's not a problem. Okay, I give some feedback, blah, blah, blah. And then the server port is created. It's based, in this case, on the base port. That again is provided, that is derived from the username. So basically, I'm just using the user ID, which is VSC 345678. No, 345, whatever. And I'm using from character 3 up to 5, so I'm just using the number of the VSC ID. I use that as a base port, and then I add something to it which makes it individual for each particular worker instance. Okay, I set some environment variables, again, based on the port number, so that makes it unique. And this I'll use for the binding. So this is where my conf directory will come from. Okay, so we create it. We create the port number file into that directory, and this yeah, you can do for all instances. And then the instance is defined and the instance is started. And as you can see, we do the binding to the specific conf directory which we just created. Okay, and then the Alpine instance is just the Alpino, Alpino server port which is used to construct the name. Okay, so depending on the service which you start, it may take a while to start. So for Alpino, it would be almost instantaneous, I think. But if you have a, let's say, sophisticated database system or a web server, it might take a while. So it's typically a good idea to just wait for a second and to check, and then to start the then starting the clients. It might be a very good idea, which I don't do here, but to check the exit status of the starting of a container. I don't do that here. My job will just fail, which is okay, not such a good idea. Okay, anyway, so now we know that our server is running or service is running, and now I have the client, and that's going to read data from a file. And it is going to then contact the server to get the data. So this is a very primitive client in the sense that the thing you do is you use netcat in order to execute this particular command here. So typically, if you have, for instance, a database thing, you would here have a database client which is active. Here the client is really straightforward. You just netcat stuff to that particular server at the right port and at the right host, which is localhost, obviously here. Okay, then basically you do that until things are done. Input is taken from a text file here, so basically each line of text is going to be input for the a part of speech tagger, which is an Alpino. Okay, so when everything is done, we just stop the Singularity instance. And again, we give it a little bit of time and then we clean up. So here the conf directory is removed because I don't care about those conf directories, of course. Okay, so that's how this would work. So this is starting the service, that's here. This is running the client, and that is stopping the service. That's it. So fairly straightforward. Okay, are there any questions about this? So you find those scripts in the GitHub repository you have the link to. Okay, important question when we're talking HPC, obviously, is performance. How much do we lose? So starting an image is of the order of half a second. Okay, that means if you have a workflow that uses a container that uses an image to do something that takes 1/10 of a second, you should probably not do that in a for loop, because that means that most of your time will actually be spent on starting up images rather than doing computation. So it's just something to keep in mind what the granularity is here. So basically that means if you do have a workflow where you have many short run times, then do that execution in the image. So basically make sure that the execution of the for loop is going to happen in the image itself, not on the host. So don't call Singularity run a million times. Put those million calls into the image. So it starts once, and then it does a million computations as soon as it started. So that's an important thing to keep in mind. Okay, so for serial code and for OpenMP, the overhead for a wall time of approximately 20 seconds is less than 1%. And for 3 minutes, it's less than 70%, than 0.7%. So basically, this is peanuts. I mean, if you just look at the performance fluctuations of a typical job, that's of the order of a couple of percents, 2-3%, sometimes up to 10%, just depending on what is executing on the node on which your job is running, depending on the load of the network, etc., etc. So this kind of overhead is negligible. So for serial code and OpenMP, you're perfectly fine. And if you look at the scaling, then you will see that the overhead for OpenMP is as good as independent of the number of threads. So for OpenMP and serial code, you're perfectly fine. For MPI, I did a few tests, one of them computing a single value decomposition and the matrix product. So basically a dgen. Okay, so this is a parallel SVD. So basically it's scale APAC. And as you can see, the overhead is a bit larger. So we have 7% for 16 processes, which is okay-ish. 24% for 64 processes is not so very good. So this is running on multiple nodes. This is PDGEM, so that's matrix multiplication, double precision. So as you can see, overhead for 16 processes is very small, and for 64 processes it's 10%, so it's quite reasonable. Now the SVD is of course a pretty expensive operation with respect to network interaction. So here network interaction is a lot more intensive than it is for the matrix multiplication. So that obviously influences the performance. These are fairly old tests, so it might actually be much better now. If I have some time, at some point I should repeat the tests, but my assumption is that it actually improved rather than decreased. Okay, so if you have a choice, obviously it's better not to use images, so not to use containers, because you do have overhead. It may be small, but you have overhead anyway, especially for MPI. So do test. I mean, and also try and get an idea whether you have overhead or not. Now, of course, if you can do these tests, it actually means that you can run the software natively without containers. And then the question is, okay, what's the point of using images anyway? So yeah, you have to kind of rely on figures you get from somewhere. Okay. So performance pitfalls. One of the things that you really have to take care about is when you use libraries and applications, that those libraries and applications are actually optimized for the hardware you're going to run on. So if you just use for computationally intensive applications, if you just use, let's say, out-of-the-box applications, your performance will not be that good. It's a bit problematic. Another thing which is important, of course, is the optimization level. So if you run it on your own laptop, and that's, let's say, an older machine, and you even build with optimization switched on, you may miss out on some performance on the cluster, because obviously the instruction set of the newer hardware will not be taken into account, and you will probably lose on vectorization and that kind of thing. So yeah, it's something to keep in mind, whether it's an issue or not. So basically, compiling your application in your image before it's actually running might be a good idea. And in that case, of course, try and use things like -x host or the GCC equivalents of that. You may lose 10 to 40% due to this, or even worse in some cases. So it's just something to take into account. Does it matter? It depends. I mean, if it takes you a month to get the software running natively, and the runtime of the whole thing is a day, okay, I can very much live with 10 to 40% performance loss. So it all depends. It is pretty crucial for things like BLAS and scientific libraries like LAPACK and PETC. There you would really lose quite a lot of performance unless you're careful. So for instance, if you just have an image which has the NetBLAS implementation of BLAS, so that's the library, basic linear algebra subsystem that gives you scalar, that gives you vector operations, matrix vector operations, and matrix matrix operations. If you have a non-optimized version of that, you're really going to suffer. So make sure that in your image, you have some decent implementation of BLAS and LAPACK. Otherwise, your performance will really be crappy. And it's easy to get good implementations in your image, so you don't have an excuse. Okay, any questions about this? Not really. Okay. So one of the, well, I would say newer kids on the block is Podman. And Podman is rather nice because Podman also allows you to build containers and run containers when you don't have privileges. And so basically on Genius, for instance, you can in fact use Podman in order to build and also run your containers. So that's a good solution if you really, really want Docker and really, really don't want to use Singularity. So it can build containers without using sudo, and it can run rootless containers, so no daemon, which basically means that the problems which you have with Docker on HPC systems, having to use sudo and having to use having a root in the container is alleviated. So the nice thing is if you're familiar with Docker, Podman has the exact same command. It's the exact same syntax, so that's easy. And this, for instance, allows you to, as I mentioned, build containers on HPC systems, if, of course, Podman is installed, and if things are configured correctly, and also to run them. So that's an alternative. Okay, so we're already at conclusions. So that's good, or not as good, depending on your point of view. So advantages of Singularity is portability, that's important, and reproducibility. So one of the things, it should be in best practices. I don't know whether I have a best practice slide. I have it with respect to performance, but not to building containers, I think. So if you look at examples of, and typically examples of Docker files, you'll always find things like, okay, my base image is going to be something latest. Okay, that's sort of nice because it means that when you rebuild your compiler, you rebuild your image, you will actually have the latest version of that operating system. Okay, but is that what you want? Because one of the reasons to use containers, to use images, is to ensure that you can reproduce things. So that means if you lose your image and you have to rebuild it, and your recipe, be it a Docker file, be it a Singularity recipe, specifies that the version is latest, you will get something else. You will not have the image which you used to generate your data. Is that acceptable? Maybe yes, maybe no. But you have to realize that at that point in time, you're not able to reproduce for certain the results you had. So personally, I really dislike the latest thing. Just put an explicit version tag there so that you're sure that you actually just get the version, the same version all the time. Of course, it's also important to keep track of your recipes or your Docker files and just put them under version control so that it's very easy to regenerate an image from a recipe which you used at some point in time. So that's important to keep in mind. It's easy to create images with Singularity. Just Singularity build recipe, done. Well, okay, Singularity build image name recipe, and you're done. And it's also quite easy to integrate images into existing workflows. So we've seen how to do it for OpenMP, so for multi-threaded applications, for MPI, for distributed applications, for services, and so on. You don't need any privilege escalation unless you have to create them. Then you have to be root, or you can do it remotely, and then you don't have to be root. And the nice thing is, it's just run as a user. There is no root user, so you can't even do a sudo in an image. That's quite straightforward. And it's quite reasonable with respect to performance and overhead. Of course, it should definitely not be used as an excuse to run crappy software or suboptimal software. As I mentioned, there are fairly straightforward ways in order to get good implementations of software into your images. Don't use NetBLAS, use OpenBLAS. Just install the right BLAS library, and if necessary, also optimize on the system, on the target system, the one you're actually going to run on. Okay. Bootstrap best practices, here it is. When you actually create your images, just install software in the default locations. Just let the make install do whatever it wants. It's no problem. Because basically you don't care. I mean, you have something which is a little bit messy. You would not do that on your own system, but it's an image. I mean, nobody cares. It has a single purpose in life, and that's running the software you're installing. So if that software is in places where you normally don't put software, who cares? Environment variables can be defined in the $environment. Of course, if you rely on environment variables such as OpenMP num threads, this of course does not go into your environment because you need to adapt that at runtime, but other environment variables can go in there. So don't bother with permissions. Everything should be owned by the system account, not a user. So don't change ownership to something. The default is just fine. That will be the root process. Well, okay, it's not root, but user process, it's fine. And then certainly do not mess with etc password, etc groups, etc., etc. That is really going to mess up your image. So don't do that unless you really, really know what you're doing. I can give you an example where I actually do that kind of thing, but normally don't do that. So again, installation should really follow a recipe, either a Docker file, which you then just use a singularize, or a Singularity recipe or an HPC CM script. Don't do that by hand, because otherwise, if you have to modify an existing image by hand in order to make it do what you want, you will have trouble reproducing things later. So just don't do that. It's a little bit more work to get your recipe right rather than fiddle with an existing image, but yeah, it's better. And that's why I also am not in favor of the toolbox thing. I don't think it's a solid solution. It's a hack. I don't like hacks. Okay, so some references. The documentation for Singularity is actually pretty good. It's split into two parts, a user guide and administrative guide. So typically you need the user guide. Sometimes having a peek at the administrative guide can be useful if you want to run Singularity on your own system. There is a Singularity GitHub repository, of course, and there is an older article that discusses Singularity as compared to either Docker or Shifter. Okay, some other things which I want to mention. One of the reasons also not to build your Singularity containers on HPC systems is that if you rely on Docker, you may have a hard time. And the reason for that is that if you use Docker IO, this is typically kept in the sense that you can do from one IP address a certain number of interactions with Docker IO per unit of time. The problem is that all traffic from universities, typically from the outside, seems to come from a very limited range of IP addresses. And that means that if a lot of people are messing around with Docker, it means that limited number of requests which you can do per day is exhausted pretty easily. So that means that you get something like, okay, maximum rate exceeded or something like that, and that you just can't use Docker IO to pull your images. So that's also something to keep in mind. Now, at KU Leuven, there is a pilot project at the moment which has a local repository of Docker images that also serves as a cache to Docker IO. And this means that rather than pulling your images from Docker IO, you can create your images in that repository and then pull them from there. So that will definitely alleviate the load on Docker IO from the university considerably. It will also cache things. So for instance, images that are often used, like the base images for Ubuntu or for CentOS or for Alpine or whatever, will already be in that repository. So you pull them from the local repository. If it's there, you get a copy. Otherwise, it is retrieved from Docker IO. So that's something that is currently in closed pilot. But if everything goes well, this will be rolled out as a service. It's still under consideration how we will make this available, whether it will be a KU Leuven service or a VSC service. If it's a VSC service, then other universities might also use that. But this is something that still has to be decided, so that's not sure. Okay, so that's one thing. Another thing which is interesting, but which is, let's say, on the midterm horizon. So we have Singularity, we have Docker, we have Podman, all have their advantages. There's also a new project which is called Sarus. And the nice thing about that is that it is, again, something similar to Podman, but it's specifically built for HPC. And what that means is that it makes it easy to ensure that performance critical libraries, such as, for instance, MPI libraries or NVIDIA libraries for GPU, are in fact more easily managed, and that you can create portable images that work everywhere. But if you run them on an HPC system under the control of Sarus, it will actually ensure that the correct versions of those libraries are injected into your container when it's running. So that's a nice thing, which is again on the horizon, but this is pretty new. So as far as I'm aware, it's not installed on more than a handful of HPC centers. So yeah, we will wait a little bit before actually deploying this. We have to test also, and so on. It needs to be configured, so it requires some work. Okay, I think that's about all I wanted to tell you. Oh yeah, that's how to create an empty image. That's no longer really necessary, but if you want to do that, you actually can create an image without anything in it. So this is just basically your image itself. You can give it a certain size. Okay, not particularly exciting, but it was necessary at some point, and I never removed the slide. Okay, is there anything you want to, well, are there any questions? Let's start with questions. No questions. Is there anything you would like to see live? Famous last words. Okay, apparently not. So then I think we can conclude here. Just before you log off, give me half a second, because I'm going to make a screenshot of the list of participants for your certificates. Okay, that's done. So, okay, thank you for attending. If you have any questions, yeah.
Sorry, a last minute question. I see that I only actually put my half name, like not the last name.
Yeah,
And
I'll probably figure it out.
yeah,
Because basically I have the list of participants, I have the email addresses, so given that your name is likely to be unique, I think it's fine. I'll
yeah.
probably figure it
Actually,
out.
it was said in one of the email, but my apologies that I didn't put my
No problem.
full name.
No problem. No problem.
Okay, thank you.
As long as it's not too many people, it's no problem. Then I can figure it out.
Yeah, thanks.
Okay.